Hello everyone and welcome back. What I want to do in the next 2 or 3 videos is talk about annuity dues, annuities in perpetuity, and talk about how to use the financial calculator to do annuity calculations. So despite the fact that, as we'll see, the calculator can do annuity calculations very quickly, you definitely need to understand how annuities work and understand the mechanics of annuities, or you will not have any chance of passing exam FM. Like most other topics, if you don't understand the topics, then good luck passing the exam. Okay, so right, let's begin. So the idea of an annuity due is basically the same thing as an annuity immediate, except payments are at the beginning of each period. Okay, so as I mentioned, for example, let's say you are a landlord, you take in rent at the beginning of each month, and immediately when you get that rent payment, you put that into an account, earning certain let's say monthly effective interest. Okay, so payments into this account at the beginning of each month is an annuity due, and that's a typical example of an annuity due. I like to think annuity dues are like rent payments, and annuity immediates, where payments are at the end of each month, are like loan or mortgage payments. All right, so the time diagram is very similar to the annuity immediate time diagram. So we have our first payment of P, payment or deposit of P, and what's the time value of that at the end of N periods? Well, if J is the per period interest rate, and this annuity lasts N periods, this is just P1 plus J to the N. It accrues N periods of interest rate J. For the payment or deposit at the end of the first period, or maybe you should think the beginning of the second period. So for the payment deposit at the beginning of the second period, that accrues N-1 periods of interest, etc., etc., until you get the payment at the beginning of the last period, and that accrues 1 period of interest. So like with rent payments, you pay rent, if it's 1 year's worth of rent, you pay rent at the beginning of December. You're not going to pay rent at the end of December for the current year. I mean, you would pay rent at the end of December for January of the new year. Okay. So here we're thinking of N payment periods, where payments are at the beginning of each period. So the last payment occurs at the beginning of the last payment period, which occurs at T equals N-1. Okay, so to get the accumulated value, you just add all these up, add everything up here, and just the usual geometric series formula after we factor a P into 1 plus J. It's going to be P1 plus J, 1 minus R to the whatever exponent this is. Here's N-1 plus 1 over 1 minus R. R is 1 plus J. And as before, just simplify the denominator, the minus J in the denominator. And you can make both top and bottom positive by just multiplying top and bottom by -1 to get my formula for the accumulated value of an annuity due, N periods, payment or deposits of P per period with an interest rate J per period. Okay, and when P equals 1, we use this notation here. And I really don't know why anyone decided it would be a good idea to use double dots for annuity dues, but that's what everyone does. So everyone in the actuarial realm, this is standard actuarial notation. So we're gonna stick with it. So yeah, S double dot and J is this formula, this quantity right here. And it's exactly what I have here with P equals 1. So you can interpret this as the accumulated value of an annuity due, interest rate J, and periods where the payments or the deposits per period, beginning of each period, is just $1. And so in summary, we also have just from here that in general, the accumulated value of an annuity due is P, S double dot, and J, where instead of $1 per period, it's P. The payments are P, or deposits are P per period. So you do want to remember double dots here means annuity due, payments are at the beginning of each period. Without the double dots, it's an annuity immediate, payments are at the end of each period. All right, so a very easy example. A landlord collects $700 in rent, beginning of each month, and immediately puts this into an account earning 2% nominal interest, compounded monthly. How much does this account have at the end of a full year if it has nothing in it at the beginning of the year? So this is really nothing to this. It's just plug and chug. Okay, so we are given that I-12 is going to be 2%, so it's 0.02. So the effective monthly interest rate is just 0.02 over 12. So remember, the effective interest rate for a period of 1 over 12 years is whatever this is over 12. 1 over 12 years is a month. So the effective monthly interest rate is just, 0.0016 and keep going. So rounding 0.00167. Okay, so the accumulated value is going to be P, 700, S double dot, N is 12, so you want to be careful because this is per month, 700 per month, even though it's 1 year, N is 12, so you don't want to do N equals 1. Dump in this interest rate, 0.00167. So it's just plug and chug, 700. 1 plus 0.00167 is 1.00167. And it's going to be 1 plus 0.00167 to the n. So it's 1.00167 to the 12 minus 1 over J, 0.00167, and you're going to get 8491 and 74 cents. Okay, so just a very simple example to illustrate using the formula. So I should mention, and if you think about it, this should not be surprising. This formula here is exactly the same thing as the annuity immediate formula, except we have a 1 plus J here. And why should that not be surprising? Well, the timeline is exactly the same as an annuity immediate timeline, except everything is shifted back by one period. And so everything, the accumulated value of all these payments are the same, except all these payments accrue one more period of interest because all the payments are made at the beginning of each period versus at the end of each period. So that's sometimes useful to just keep in the back of your mind that really these formulas are exactly the same except this 1 plus J here for the annuity due. Because everything is basically the same for an immediate due versus an annuity, an annuity due versus an annuity immediate. Just with an annuity due, all the payments accrue one more period of interest. Okay, so let's get into a more interesting example. And this is actually, if you have the Groverman book, this is 2.1.13S. So it's a former actuarial exam problem. Okay, so a person needs to buy an item that costs $400 today, and the person needs to buy this at the end of 20 years. The item's cost inflates 4% each year. To finance this item, the person deposits $25 into an account at the beginning of each year for 15 years, earning 3% effective annual interest, and makes additional deposits of X at the beginning of years 5 through 10, 5X. So here I should mention that's implicit that after these 15 years, the person is just leaving money in this account for the next 5 years, at which point the person will take what's ever in the account and use it to buy this item. All right, so this is not a particularly hard problem. It's just there's a lot of moving parts. So you just got to be a little careful putting things together. Okay, so let's do this problem. Sorry about that, give me one moment. Okay, so move this up, move this out of the way a bit. Okay, so first of all, so the item cost now is $400. So in 20 years, well, there's not a whole lot to this. The price, the cost is $400. It inflates by 4% every year. So just, and it basically accrues, if you will, 20 years of interest at 4%. So this is going to be a bit 876.44926. So this is how much I need, $844.45. This is basically how much I need at the end of 20 years. Sorry, I'm just going to put this over here. Okay, so let's just draw a timeline of the whole situation here. That's good enough. So there's 20 years, 0, 1, 2, well, silly here, let's do 3, 4, 5. Okay, so right, let's keep going until 9. I'm just basically putting important dates here. So 9, and I'll explain why I'm putting these numbers up in a second. Okay, so it's $25 that you're putting into this account at the beginning of each year. 25, and then at the beginning of the 5th year, which occurs at t equals 4. So this is year 1. This is year 2. Sorry about that. So let me just put a line here. Right, so this is 2 to 3 is year 3, 3 to 4 is year 4, 4 to 5 is year 5. So at the beginning of year 5 occurs at t equals 4 on the timeline. We make additional deposits of X all the way until we get to the beginning of the 10th year. After which time we just keep going until we're at the beginning of the 15th year, which is when our last 25 payment is, which is at t equals 14. Okay, so, right, so, okay, so actually, sorry. What I'm going to do is let's break this up into 2 annuities. Let's just break this up into the 25s, and then we'll break up the X's as its own annuity. Okay? So remember when we did annuity immediate problems, that's how we handled multiple payments. We just broke everything up into separate annuities. All right, so and yeah, I'm going to have to give myself more room for these separate annuities. Okay, so in particular, let's do the 25. So 0, 1, go all the way to 14. Okay, and I'm going to put a 15 here. I'll explain why in a second. So for the 25 payments, 25, 25, 25. So for an annuity due, it's always we're finding the accumulated value 1 period after the last payment was made. So at the end of the 15th year, the accumulated value is just plug and chug into a formula, 25 S double dot 15, and the interest was 3%, so it's 0.03. And then this quantity here accrues 5 years of interest, because this amount sits in the account for 5 years. So this is going to be 25, try to squeeze this in here, S15, 0.03, 1.03 to the 5th. Okay, and this is going to be, if you just plug into your calculator, 555.2019. Right. And I just want to clean this up a tiny bit. Okay, so now let's do the X payments. So the X payments occur when t equals 4 all the way up to t equals 9. And then again, I'm going to write t equals 10 here, so it's x, x, x. So there's 5 of them. Sorry, there's 6 of them. Or rather, there's 6 of these payments. Okay, so at the end of the at the end of the 10th year, this accrues to XS6 0.03. And we don't know what X is, but that's all right. And if there's a confusion whether this should be 4 or 5, as I like to say, there's no shame in using your fingers. So we can use our fingers, 4, 5, 6, 7, 8, 9, which means 6 payments. I mean, you might think, well, it's 9 minus 4 is 5 payments. Doing little things like this to me is what is a little tricky in this course. But again, you use your fingers, you'll see it's 6 payments. Okay, and like before, this accrues 5 periods of interest. So at the end, 10 periods of interest. So at the end of the 20th year, this is going to be whatever this is, times 1.03 to the 10th. And that's going to be 8.953,792. Actually, let's just round up to as usual, to the nearest 5 places times x. Okay, so, so we need 876, the end of 20 years, to buy this item, 44926. And we're paying for this item by what's in the account at the end of the 20 years, which is 555.2019 plus 8.95379. So subtract 555.2019 divided by 8.95379, and you get that X is going to be $35.88. So again, not a terribly tough problem, but there's just a lot of moving parts. So, okay, so let's continue on. Okay, so so let's get the annuity due present value formula. So the idea is basically the same as before. So at t equals 0, the t equals 0 payment is worth p, because you're not discounting that at all. At t equals 1, at the end of the first period, you discount that by 1 period, that's p new, where new is a present value factor 1 over 1 plus j. The payment or deposit at the beginning of the second period, you discount that by 2 periods, so that's p new squared, etc., until you get the last payment at the beginning of the last payment period. That accrues, and you discount that by n minus 1 periods. So you just add all this up and use your geometric series formula. And my apologies, there should be a P here. So I'll fix that, but there definitely should be a P here. So the present value of an annuity due is P A double dot NJ, where A double dot NJ is what I have here. So it should be P times this whole thing using a using the geometric series formula. So actually, let me fix that really quickly. And yeah, if you're ever curious how I make math symbols here, well, here's you can learn how I do it. It's something I love called Iguana Tech. It's completely free. And just, I would put it in Google if you're curious what it is. It's just literally how to make LaTeX in PowerPoint. Anyway. Yeah, so it's P times this whole thing here, and A double dot NJ is this whole thing here without the P. Or you can think it's the present value of an annuity due, where the payments or deposits are $1 per period. And right, so I also want to discuss, like we did before, an important interpretation of the present value of an annuity due. So let's say you're in the situation, I'll do an example of this in a second, that you want to put money right now into an account so that you can make rent payments of P at the beginning of each month for, let's say, 1 year. And let's say you have a per month interest rate of J. So the amount you need to put in the account so that you can just pull out money just so that you can pull money out of the account when rent is due and have exactly enough money to just do this and not a penny more or less is the present value of this annuity. Why? Well, so how much money do I need to pay rent if rent is P? I need P for this month. Okay. So how much do I need in the account? How much do I pull out of the account to pay for rent in 1 month? Well, I need P new, because if I put P new in the account, it accrues 1 month of interest, I'll have P in 1 month. How much do I need in the account to pull out in 2 months to pay rent of P? I need P new squared, because that will accrue 2 months of interest, and in 2 months I'll have P. So add all these up, and if you think about it, you'll have exactly enough money to pull rent payments out when they're due, and you won't have a penny more or a penny less to do this.